We've seen how to use classes to organize the data for our programs. One class may have instance variables that are lists, or it may contain another class as one of its instance variables. This is known as composition. One of the main benefits of classes is you can organize the data and methods together. As you may have discovered when writing more complex programs with only functions, you may need to pass many parameters and have multiple return values so the function has all the data it needs to process and can return all the values it updated. By using a class with the data as instance variables, we can make those functions methods, and we won't need to pass all the parameters and have as many return values since the functions can update the instance variables directly. In addition to using a class to model components of our program, we can use a class to model the data that you might otherwise store in variables in your main function as we've been doing. We can treat the program or application as an object and store the data as instance variables. We can still use the top-down design techniques we learned earlier and make methods for each subtask. Here is what we want our calculator to look like. We will use the strategy of encapsulating all the data for it in a class and use methods for each subtask. A calculator app is an event-driven program. It waits for the user to press a button and then updates the display based on the button that was pressed. This process is then repeated. We will need to store each button so we can check which one is pressed. Since we know how many buttons there are, we could use separate instance variables for each one, but as we saw with the dice pips, it is better to store them as a list so we can process them with a loop. We'll now look at the code in PyCharm. The constructor creates the window. We set the window's coordinates so we can easily place the buttons. We need to save the window as an instance variable so we can use it to get mouse clicks in a different method. Next, we call the helper methods to create the button and display for the calculator. We could have placed all that code in the constructor, but we'll follow the principle of breaking a problem into subproblems and write a function or method for each subproblem. The createButtons method makes each button and stores them in a list. We'll use the button class from an earlier video. Since most of the buttons are similar, we'll use a table to describe where each button should be placed and what its label is. We may have mentioned tuples before, but I think this is the first time we've used them. A tuple is a Python sequence type, so it supports the same operations we saw with strings and lists, such as indexing, slicing, iteration, concatenation, and repetition. A tuple is like a list except it is immutable. Once you create it, you cannot change it. As we saw with strings and lists, you can reassign a name to a new tuple, but you cannot modify the tuple. This allows Python to implement it more efficiently than it can a list. So if you don't need to modify it, a tuple is preferred over a list. Tuples also support the list methods that do not mutate the objects such as index and count, but obviously the methods such as remove, reverse, and sort that mutate the object are not supported by tuples. Tuples are designated with parentheses, and the items are separated by commas. Here we use a tuple of tuples to designate the information for each button. The three values indicate the x and y coordinates and the label for the button. We can now iterate over the tuple and unpack the three values into the variable names cx, cy, and label. We use those to create the button and append the button onto the end of our button list. After creating the buttons that are all the same size, we create the larger equal sign button at its location and append it onto the list of buttons. We can now iterate over the list of buttons and enable each button since buttons are created in a disabled state. The createDisplay method creates the display as a text object and sets the font and color for it. We save the text object as an instance variable so we can get and set the contents of it in later methods. The getButton method is used to wait until a button is pressed and returns the string of the label for the button that was pressed. After waiting for a mouse click, we iterate over each button. We check if the click is inside the button's rectangle using the button's clicked method. If this button was clicked, we return the string for that button. Remember that as soon as a return statement is executed, the function ends, so as soon as we find a button that was clicked, we stop checking the later buttons in the list and return. Note that if you click inside the window, but not inside one of the buttons, the return statement will not be executed. So after checking all the buttons and finding that none were clicked, we start the while loop again and get another mouse click. This calculator will work a little differently than most calculators you've used. It displays the full expression in the display, and then when you press the equal button, it uses Python's eval function to calculate the value of the expression. The processButton method gets the current string in the display. If the user pressed the C key for clear, we set the display to the empty string. If the user pressed the backspace button, we chop off the last character from the string and put that result in the display. If the user pressed the equal button, we use the eval function to calculate the result. Note that it is possible to enter an invalid expression. Because of that, we use Python's exception handling and display error if the expression is invalid. If the eval function succeeds, we convert the result to a string and display it. If the user pressed one of the other buttons, which are the numbers, operators, and decimal point, we simply add it on to the end of the display. We create a new string with concatenation and set the display text object to that string. The run method is now simple. We wait for a button to be pressed and then process it. We do this with an infinite loop, so the only way to exit the program is to use the operating system's window close button, or kill the process using the operating system's tool to do that. We'll run it and see that as we press numeric and operator buttons, each one is added to the display. If we press the backspace button, the last character is removed. Pressing the equal sign uses the eval function to calculate the result, and the display is updated. If we enter an invalid expression such as 2 plus times 3 and press equal, we see that the exception handling catches it and it displays error. This program should give you some ideas on how you can apply this approach of creating a class for the application to a variety of different problems. We used the top-down designed approach to break the problem into subproblems and used methods to implement each subproblem. We stored the data needed in multiple methods as instance variables, so we didn't need to pass numerous parameters to each method or return multiple values.